So this talk. Oh, so sorry. So first of all, I want to, since this is the last talk, I want to thank Anton and Maxime for the opportunity to come here and give these lectures. It's been, so far, it's been really a pleasure, and also, kind of an honor to have the opportunity to speak here in front of this audience.
We rather have to thank you because it's your teaching semester and you came here for basically 3 days during your teaching semester, which is not so easy. So thanks a lot.
Like Maxime's talk in the morning, this one will be a little bit of a hodgepodge, a collection of things, but I want to start by sort of restating the thing that I stated at the end of the last lecture. So let's recall where we were. So again, we had this compact curve C, and we had now not just a quadratic differential, but some collection of differentials, sections of various powers of the canonical bundle of C. Sorry that this K is not the same as that K. And maybe with poles, maybe without, but for safety, I mostly talk about the case where they have poles. And I was, so from this data, and from this data in a phase, we constructed some gadget that I called the S-wall network. I don't want to repeat the definition of the S-wall network. All I want to say about it right now is that, so interesting phenomenon is that it's some special theta phi 2 up to phi k. Let me give this S-wall network a name. Let me call it W theta. W theta of phi. I guess I'll write a vector phi for this tuple. So at some special theta in phi, W theta of phi changes topology. And what I mean precisely by topology, as I said last time, is a little bit subtle. It doesn't quite mean the isotopy class. It's something a little bit weaker than that. But for example, you can understand it by looking at this path lifting rule and asking, when does the path lifting rule jump? So at any rate, we had this phenomenon that at some special values of these parameters, this thing would change topology. And exactly at those values of the parameters, there's some special object that appears. And I just want to now restate what those special objects are. So, those theta phi, some special object appears. Some special object exists, which I'll call a finite. Well, let's call it a BPS network. Okay. So the definition. So a BPS network is a collection of trajectories on the curve, trajectories on C, such that, well, okay, so it's some collection of trajectories, but they're not generic trajectories, they're solutions of a differential equation, the one I wrote last time. So each trajectory is, well, what I called last time an I.H.É.S trajectory. In other words, e to the I theta lambda I minus lambda j is real on the trajectory. Right, where theta now is this single fixed theta. So all of these things, the individual strands are obeying different equations because they have different I and j here, but all for the same phase. So that's the first thing. It's made up of these I-J trajectories. But the second thing is that they should be kind of finite, and what I mean by finite is that they don't just run around the surface forever, but rather they end. And the ways in which they can end are quite limited. So, trajectories can end, well, let's say I.J. trajectories in this network can end on the I.J. branch points. That's one possibility. So that's a sort of natural end for these trajectories, because actually the differential equation that they obey becomes singular at that moment. So it's sort of natural to have them end there. Or they can end at these kind of three-string junctions. Three-string junctions. This is the generic thing. You can imagine sort of also higher valency junctions. That would be kind of an accident. So let's assume that phi, I take phi to be generic enough. So higher valency won't occur for generic phi. I think it'll be clear what the how you extend the definition to higher valency. So what's a three-string junction? So the junctions look like this. I have an I.J. trajectory, a J.K. trajectory, and and a K.I. trajectory. So here, yeah, sorry. This thing is not only real, but real and the trajectories are oriented, and you think of them as being real and positive. So then I have a definite convention whether this is I.J. or J.I. And if I choose my orientation so that all three are pointing in, then the junction has to be like this: I.J., J.K., and K.I. So if you like, the sum of the lambdas at this point is 0. So those are the rules. And so you can make all kinds of topologies. Well, okay, first thing, so if k equals 2, then the only possibilities are the two that we, the two that I was talking about earlier, the two that are kind of well studied. So you can have this, or you can have just a closed trajectory. But nothing else. Oh yeah, sorry. Right. So each trajectory is an I.J. trajectory. The trajectories can end only in these restricted ways, and the whole thing should have finite total length. So that each strand should have a finite length. So that forbids you from having just a thing that runs around the surface forever, or a thing that goes down to the poles. Those things would have infinite length. But this is allowed and this is allowed. So for k greater than 2, there's many more things that you can have. So you can have. Well, the simplest new thing is the thing that I actually showed a picture of on the computer. The simplest thing you can imagine is this, but then of course you can have, much more complicated trees. Well, you can have, well, all right, let's have one more tree. So you can have sort of arbitrarily complicated trees. Even for k equals 3, this can happen. You can have also things that have sort of combined trees and loops. So you can have something like this. It has a junction here, and then the string goes around and comes back. This, you might say, looks funny because it should have been, at this junction, it has to be an I.J. string, say. If it's I.J. coming out of here, why is it not I.J. when it comes back to here? But the point is that there's some global monodromy in these labels, right? These labels are determined by a pair of sheets of the spectral curve. So if there's some global topology here, there's some branch points inside of here, when it comes around, it can come back to a string of the correct type. So this kind of thing is allowed. And then, you can imagine sort of arbitrarily complicated things. You have a loop in the middle and another loop here, and probably even other topologies. Well, okay, anything that's allowed by these rules in principle is going to be counted. And so the claim is, that there's going to be a new kind of Donaldson-Thomas invariant that's counting these more complicated things. Well, the Donaldson-Thomas invariant that we said are omega of gamma, so I should tell you what's gamma here. So now I have to, so recall the spectral curve.
Sorry, could you remind, they're all oriented? All
No, not oriented. Then if you put I.H.É.S, then you put orientation.
Yeah, that's right. So they're oriented only in this sense. So the choice of once I write it I.J., then I fix the orientation.
Yeah, but in fact these objects are really curves, homomorphic curves with boundary on Lagrangian manifold, on Cartesian boundary curve, with a real symplectic form. It's some limit. It's the same as object.
Right. Okay. So there's another geometric picture of these things where I think of it as being.
Okay, with very small strips and
yeah.
Boundary, yeah.
Yeah. Let me draw that picture. Okay.
Yeah.
Okay. I'll draw that picture in just a second. Yeah, I agree. That's a useful picture. But that's going to involve this spectral curve anyway. So we had this spectral curve, which was given by this equation.
Can you?
Sorry, just 1 second. Yeah.
Probably a cooling question. Can you say a correct sentence using the word ribbon graph?
The ribbon graphs. No. Yeah, definitely ribbon graphs. Yeah.
Yes.
You mean you want me to thicken these things a little bit to have an I and a J?
Yeah, because
what happens at the edges then? You have a...
Yes. You're sort of requiring the I index travels around like this, and the J index goes around like this, and the K index goes like this.
Yeah,
that's the picture you want?
Yeah, the interior will homomorphic curves with boundary on spectrum.
Right.
Sorry, maybe one more question. This tripod thing, is it imaginable that this trivalent curve can be perturbed triangle to a genus 1 case sometimes? So it's not generic situation, like have an L, you have Ki, Jk, Ij, you have L goes like triangle around the...
Oh, you're saying that this could be right. So if I have that tripod, that could be a limit of this,
Yes.
where the loop is shrinking to zero
Is it a generic
size.
situation or not?
It doesn't happen generically.
Doesn't happen.
Generically, if you have a loop like this, the way that it ends, yeah. So good. So that's a good question. So suppose I have a loop like this. We should ask the same question we usually ask, right? Whenever there's a loop that's sitting in really a one-parameter family, and in fact, the way that these things really enter, at least my version, the version of the story that I'm describing, it's not so much these generic ones that enter, it's the boundaries of the family. So you should ask, what are the boundaries of this family? But what the boundaries are, in generic situation, is just something where this loop grows enough that it runs into a branch point. And similarly, when it shrinks, it typically doesn't shrink all the way to zero size. There's some branch point inside, and it winds up ending on that internal branch point.
Right, because it cannot be round if it's
right. So typically the end of this family is some very small guy like that.
So it requires for double zero or what? To have this?
To have it collapse exactly to zero?
Double zero?
Actually, I haven't investigated. So yeah, I think it won't generically happen, but I can't. Yeah. So as I say, this is still a little bit of experimental science, but I'm pretty sure that's. Okay. So I'm trying to describe the Donaldson-Thomas invariants attached to these things, or at least I'm trying to tell you what the charge lattice is. Well, Maxime already said what the charge lattice is, but I just say it again. Given one of these finite BPS networks, let me call it S. There's a corresponding, the same thing as we had before, call it charge, gamma S in the first homology. So again, I could take the prim part here, but I'll just take the whole first homology. There's a charge in the first homology of the spectral curve, which you get by sort of the same game as we did before. you just lift each strand now, each trajectory in S. So lift each ij trajectory in S. I want to lift it to, so if I have an ij trajectory down on C, I'm going to lift it to the cover. I just lift it to something on sheet I. So it's lift on sheet I, and also it's preimage on sheet J. So this one, I'm lifting to the union of these two with opposite orientations. Now that typically, if I just look at each strand individually, that lift, of course, won't be something closed. But the conditions that we put are exactly the conditions that guarantee that the whole thing sews up into a closed cycle. So each trajectory lifts to a one chain, and the union of these one chains is gamma S. So for example, when if the thing goes down to a branch point, then of course you see that there's then it lifts to something on sheet I, something on sheet J, so there's no boundary here. And similarly at the junctions, our condition at the junctions exactly arranges that these things sew up. Okay. So the picture is going to be so the dt invariance in this setting will be omega of gamma should be counts BPS networks whose charge is gamma. Now counts, of course, is a sloppy word. We have the usual problem of dealing with multiplicities, right? When you have a family, what's exactly the contribution from that family? So here, I won't tell you a complete answer. I'll just tell you some things that are already known. In principle, it's all determined by the same kind of analysis I showed you in the case of k equals 2. So for example, it's clear what the answer is going to be for a tree. So for any of these trees like this that have no moduli, you'll get omega equals 1. So just isolated closed loops will contribute exactly the same as they did before. Contribute -2 omega of gamma. And I can make a conjecture about what the general thing will be. Let me not make this conjecture. Okay, at least you can say this much for sure.
But do you expect it for even more complicated, since you get only finitely many non-zero omegas?
I don't have. You mean for a fixed spectral curve?
Component, yeah, for fixed connected components in the space of this networks, do you get polynomial things or form for series?
No, I would have thought it contributes to only finitely many omegas. I mean, so far on this have been pretty simple examples, but okay, that it's a guess, but my guess is that that each of these things, for any particular topology here, contributes only to finitely many omega.
For multiple colors.
Right, you're wondering whether it also contributes to omega of 2 gamma, 3 gamma, 4 gamma, so on. Yeah, I don't think so, but it's possible. It's possible for that to be wrong. Anyway, but the way that it'll be determined is by exactly the same kind of analysis that I showed you for A1. You just use this path lifting rule. And as a consequence of that, because of the way they're determined, it'll be automatic that they obey the wall crossing formula, just the same way as they did for A1. So these omega of gamma, call this a conjecture. Call this a conjecture, but I've kind of sketched for you the proof already. So these omega of gamma obey. Well, the conjecture should be about some precisely defined object. So these omega of gamma suitably defined by some definition which extends these two facts are going to obey the Savage-Sutherland wall crossing formula.
Is the contribution purely determined by the topology of the network?
I think so. I mean, the way that you calculate it makes it pretty clear that only the topology. Yeah.
Yeah, but if you have family of networks, you get complicated parameter space of networks, which is...
Well, it's complicated parameter space, but it's, see, the contribution only comes from the ones that are on the boundary.
Yeah.
So, I mean, really the question is, the only real question as far as I can tell is, suppose I've got something like this. Right, I'm not allowed to have any actual closed loops that aren't interrupted by a branch point. Because if there were, it would be a modulus. I would push it out.
Really kind of rigid objects, yeah.
Yeah, in the end, it's a rigid thing, and I think the only question is really what sign does this give? It probably either gives +1 or -1. I would guess that it gives -1 to the number of loops, and so you just have to. So that would suggest that each one has 2 boundaries. So it would suggest the contribution from the whole family would be -2 to the power of the number of loops. But that sounds a little funny when you say it that way, so I...
But you don't expect contributions from non-boundary but special points, for example, when you have some flexibility, some one-dimensional family, then one bounded edge can be contracted and get to the other edge. You have a special curve which is 4-valent. You don't expect contributions.
Oh, so you're saying something like this?
Yes.
So you're saying, suppose I have
Yeah.
this thing and I contract it to... No, but this doesn't happen, so... I mean,
no. You should have genus for that. You should
genus.
Genus for that.
What do you want me to do? You want me to put...
To have it generically, you have to have genus, yes.
Okay, family, you need loops, yeah. Okay.
Yeah, exactly. So that's why I was confused. So okay, you want me to draw this one, and now...
And then one of those edges get contracted.
Yes, small edge.
Lose this
edge.
edge.
Contracted, yeah.
Oh, as this thing gets bigger? Okay, good. So as the loop gets bigger, it can bump into this.
Yeah, it's also kind of isolated object.
Because there is a similar situation in tropical geometry, and then such things do contribute to the intersection number.
All right, so I'm glad I haven't tried to state something more precise than this. So as I say, we haven't systematically studied the parameter space of these objects. So the thing I do want to say about these things is that, from this point of view, this is addressed sort of to the flat surfaces community. So from this point of view, these things look absolutely equally important as the trajectories of quadratic differentials. And so they're sort of reasonable objects of study, and you should ask, I think one should ask all the same questions that you ask about trajectories of quadratic differentials. Like, for example, as the length goes to, imagine you just do a compact curve with no punctures, you could ask how many of these things are there with length less than some finite number. You could ask for the asymptotics of that as L goes to infinity. That, I know, was a very fruitful question in the world of quadratic differentials, and I suspect it would be an equally interesting question to ask you. Okay. Okay, so I think that's all I wanted to say about these. Well, I would say more if I knew more, but I think that's all I can safely say about these things. Maybe I'll show one more picture here. So,
Yep.
So just to illustrate the kind of phenomenon that happens, even in what limited stuff we've explored. Let's see, is it turning? What I'm going to show you is how the loop can appear even in a place that has no topology. So in the case of the quadratic differentials, when you get a closed loop, it always has to be surrounding something, some branch points or some
genus.
Or some genus or something. That's right. But here you can get a kind of more interesting thing. So this is a picture in the K=4 theory. This is a picture in the K=4 theory where I've taken, again, the quadratic differential to be very big and the other differentials to be quite small. So we're sort of close to the locus where the thing was just governed by a triangulation. And so what we've got is what would have been just a single branch point in the for the quadratic differential has been sort of broken into 6, which are sitting here, kind of arranged in this triangle. And then each of them is shooting out these walls, and then there's a quite complicated sort of secondary structure of extra walls that emanate from the intersections. So now, as you adjust the phase, so I'm sitting sort of quite close to a critical phase where something interesting happens. And as I adjust the phase, the structure is getting sort of more and more dense. And so you're again approaching a situation which is similar to what we had for the quadratic differential phi 2. So for phi 2, you had a cylinder which was sort of getting filled up more and more by trajectories. Now you might think it's hard for something like that to happen here because there's nothing that the trajectories can kind of wind around, right? You know, each trajectory has to go off to infinity. So how can you get some kind of dense structure filling up? But as you see here, the way that it happens is that the trajectories are sort of, how can I say it? Well, the trajectories are emitted from, so here's a trajectory being emitted from the branch point, generates a secondary one which goes here, generates a tertiary one which goes here, and so on, sort of winding around infinitely many. So in the limit, when I go very close to the critical phase, this thing will actually be winding around infinitely many times. And so it generates, so all the complexity that was there for the quadratic differential with some topology, here can be there even without any topology. Okay, that's just that's a picture stuff. Okay, I think that's all I want to say about that. So now I want to go to something else. Right. Okay. So just as in the, so as for k equals 2, the S-wall networks give a sort of non-abelianization match from, sorry, let's see, and any S-wall network gives a sort of non-abelianization map from GL1 connections on sigma to GLN connections on C, and let me remember now what I didn't remember last time. They're actually GLN connections on C decorated with a little extra structure, decorated with a flag. A flag in the space of projected flat sections around each puncture.
These are twisted as before?
Yeah, twisted, sorry. That's right. Twisted. And twisted. But then as before, you could get rid of that if you were willing to use a spin structure on sigma and C, so somehow that's not, well, it's there, but it doesn't fundamentally change the story. So, sorry, I was calling this K. So at least, so for some special S-wall networks, not the most generic one, but for some special ones, this non-abelianization map has been seen before. Let's go over here.
And is this non-abelianization map some kind of formal series or?
No, it's a real thing. I mean,
It's finite expression, yeah?
Yeah.
Because this S-wall network is kind of not infinitely complicated.
That's right. That's right. This is a thing that you can really do. In the case with poles. So without poles, it would be more complicated. It must still exist, but I wouldn't claim to have constructed it. So now, so for some special S-wall networks, namely the ones where phi 3 up to phi k are generic, but they're much smaller than phi 2. This non-abelianization map is already known to be 1-to-1 onto a dense open subset. In the moduli of these GLK connections. Let me just call this M. It's known to be 1-to-1 onto a dense open subset of M. That's once again because fortunately Fock and Goncharov already constructed the inverse. Which I'll call the, so that's abelianization. Okay. So the S1 network gives us this map from non-abelian connections to abelian connections. And so now I want to connect a little to something that Maxime talked about in the morning. Just a priori, you might ask, have I ever seen something like this before? A way of taking non-abelian connections and making abelian ones out of them. And the answer is that, yes, people study that all the time, not for a connection, but for a family of connections. Oh, I should say, sorry. So it's known for some special S1 networks, but the conjecture is that this is always the case. And you might be able to prove it just by starting from these special networks and sort of making the coordinate transformations one after another.
So you get birational map,
yeah. So if I change the S1 network just by by the effect of one of these special trajectories, it just gives some simple birational map with these tori. So you would expect that if this works for one network, it works for all of them. Right, so now I want to talk about this other way of abelianization connection, which is WKP. So suppose we're given a family. So we start now with the non-abelian one. So suppose we're given a family of GLK connections. And the family is of the form, so the connection will be called nabla. Nabla zeta, it depends on a parameter, zeta. Just of this form. So I have, that is the family of connections that has a first order pole, and I've kind of isolated the pole and writing it like this. So phi is just the GLK valued matrix. One form, sorry. And D of zeta is some family of connections of GLK connections. But this is GLKC. I always mean GLKC. Well, maybe for this part it doesn't even matter. D of zeta is some family of GLKC connections, which is regular at zeta goes to 0. So I'm just kind of isolating the whole part. So the sort of standard analysis of, so what do you want to do? What you want to do is to study the flat sections for this connection, but in the limit where zeta goes to 0. Well, I guess I should call the solution also psi of zeta. So nabla zeta psi of zeta equals 0. in the limit zeta goes to 0. But what would be the kind of naive thing you would think, right? If the equation was just literally phi over zeta plus d, imagine that, so the idea, sort of very naive version of the idea. So imagine that, well, first of all, imagine that this phi is generic, so we could diagonalize it. So imagine that phi is diagonal. Just lambda 1 up to lambda k. Imagine that you've diagonalized it. And then after diagonalizing it, so we're always free to do that, but the question is, what will the connection look like exactly after diagonalizing? Imagine that it looked like the simplest possible thing. That it became literally just, in the diagonal form, that it literally just looked like phi over zeta plus d, little d. This connection d of zeta just becomes little d, some local trivialization. So then, of course, it would be easy to write, then it would be easy to solve the equation. So it's completely diagonal, so the solutions would just be, well, we could write a basis of solutions, say psi I of zeta, would be just, well, I just have to take the exponential of the integral of the ith eigenvalue, say exponential of 1 over zeta times the integral of lambda I, and then multiplied by the ith basis vector. So this is just basis vector. For R to the k, C to the k. Elementary basis vector. So that's a sort of naive form of what the solution could look like as zeta goes to 0. Now, of course, you know that the actual connection is more complicated than that, but you kind of feel like, well, this is the dominant part.